good morning or good afternoon, wherever you are. Appreciate that. As you know, the workshop is about directivity-based probabilistic seismic hazard for the state of California. I have only a few slides to set the stage, and then we move on. Before we start, I want to thank especially Linda, Nick, and Sylvia, who have been working on these things for a few years now. And they did the heavyweight also in the last few years. Also, we would like to thank Directivity Modelers, Brian Cho, Jeff Bayless, as well as Badi Roshandel. They have been contributed to the project, as you will see soon. So the project has been partially supported by California Energy Commission, PG&E, Caltrans, SoCalGas, California High-Speed Rail, as well as LA Department of Water and Power. So the goal of this project has been to merge three pieces, which means directivity models, NGM-WES2 model, and USEF3 model, and generate and run PSHA for the whole state of California, which, as you will see, this was not an easy task. And then after the computation was done, Sylvia generated for the first time directivity-based PSHA maps and results for the state of California. So there were massive PSHA computations for this task. More than 19,000 sites were used to compute PSHA with and without directivity, as you will see. And then a web tool was developed to interactively access the massive data and maps. So today, Linda and Nick will go over the details of the computational development of the PSHA with and without directivity. And Sylvia will present the online tool to access maps and data. So please enter your questions into chat, and we are going to go over the questions as much as we have time. Please mute yourself during the presentation, otherwise it's going to be very noisy. Thank you very much for your participation. I will now pass it to Linda. Give me a few seconds that I stop sharing. And now I think, Linda, you can share. Thank you.
All right. All right. Good morning. So I'm assuming everybody can see my slides. As Yusuf said, this is the product of a multi-year project, and we would like to thank the Directivity Working Group members formed of Directivity Modelers as well as the funding agencies. So as a background to this study, the goal was to compute hazard calculations, ergodic hazard calculations at 19,316 sites across the state of California. The sites are shown in this grid of points here. In red, you see the USEF3 faults, and in blue, it just shows pipelines. In this study, we have used the USEF3 source model. We are using what's referred to as the true mean solution, which is the solution that allows one to calculate the mean hazard. For sites in Northern California, we're also including the Cascadia subduction source model based on the USGS model. In terms of ground motion characterization, we're using the 4 NGA-WES2 models for crustal sources, Abrahamson et al. 2014, Campbell Bozornia, Bohr et al. As well as Chu and Young's. For subduction sources, we're using the newly developed NGA submodels for the Cascadia-specific region, as well as the original BC Hydro model. And for both crustal and subduction GMPEs, we included the epistemic uncertainty in the median prediction. For the no directivity hazard, so first we calculate the hazard at all of these sites without directivity for a series of VS30 values. between 180 and 1100 meters per second, as well as for estimates of site-specific VS30 and site-specific basin depth wherever we have reliable estimates of those values. The hazard was computed for 22 periods between 0.01 and 10 seconds, as well as PGV. And this was all implemented in a modified version of HAZ45. So for the use, now from here on, I'm just going to focus on the directivity implementation, which is the topic of our meeting. The challenge, as you know, for implementing directivity, especially with the USER3 fault ruptures, is that the complexity of the fault ruptures in USER3 really makes it difficult to implement directivity models, which are developed for a lot simpler type of ruptures. For instance, about 93% of the fault ruptures in USER3 have gaps or step overs, and sometimes you can have up to 9 gaps per rupture. The gap distance at the ground surface can be up to 39 kilometers. Of course, at some depth, the segments have to be within 5 kilometers of each other, according to the rules for the development of USER3. In addition to the fault gaps, which makes it challenging for the directivity models, we have in a lot of cases relatively large changes in dip and rake angles within individual ruptures. And since our study is a regional sort of large-scale study, we couldn't be spending the time looking into every single rupture, so we needed to find a solution that would work pretty much across the state. So to do that, we really our goal was to find an approach for implementing directivity in addition to simplifications in the fault ruptures that are technically defensible and that are also practical, that allows us to sort of do the computations for a large number of sites. We also wanted simplifications in the source models that makes it possible to work with any of the directivity models, because some models are simple, other models are more complex and have different criteria. So to do this, we came up with a scheme of dividing the USER3 fault ruptures into 2 types of ruptures, what we call multi-fault ruptures and multi-segment ruptures, and I'll talk more about each one of those. And we have adopted a smoothing over the fault gaps such that we always created a continuous fault rupture for the simplicity of implementation of directivity. I want to emphasize that for the no directivity part of the hazard calculation, the entire USER3 source model was used as is without making any simplifications. So the simplifications were only used to compute directivity parameters. Our first group of fault ruptures we call the multi-fault ruptures. This is by definition a rupture that occurs on 2 or more non-contiguous surfaces, with each surface having its own hypocenter. In these cases, what we screened the entire database of USER3 fault ruptures and classified ruptures as multi-fault if they satisfied these 2 criteria. If they had a change in the dip angle between consecutive subsections of more than 50 degrees and a change in the rake angle of more than 30 degrees. So we have judged these ruptures to sort of be kind of on the more extreme side of ruptures, and that they would need to be treated a little separately. And so when we screened out the set of ruptures, we then proceeded to generate fault strands for each rupture, and we put the breaks at whatever this condition is met, as well as at gap distances greater than 10 kilometers for this set of ruptures. So doing that sort of gave us about 178,000 multi-fault ruptures. So it's really a relatively small proportion of the entire database of about 1.6 million ruptures. But for those, we treated them separately because we thought that they needed to be, they're different enough from the other ruptures. Just some statistics. We have in these multi-fault ruptures, we can have up to 6 fault strands per rupture. We still can have gaps within those ruptures that we need to proceed and treat differently. And they are distributed between mostly strike slip and dip slip ruptures with some oblique cases. For the individual fault strands that do contain gaps, we then proceeded to smooth those using our smoothing spline algorithm. So here is an example of a multi-fault rupture. So this is a single rupture in USOR3 with a magnitude 7.9. You can see it's got 6 fault gaps. The individual colors show the different fault strands within one rupture. So this is where basically the points where this was flagged as multi-fault rupture because of large changes in dip and rake angles. So you can see within one fault strand, we still have fault gaps that we needed to deal with. On the other hand, this is another example of a rupture. This one, even though it does include a large fault gap here, it's still not flagged as a multi-fault rupture because it didn't satisfy the 2 criteria. So this is just to say that the multi-fault ruptures do not screen out the ruptures with large gaps. Now, having screened out the multi-fault ruptures, we are left with what we call multi-segment ruptures. These are the ruptures that are sort of have no gaps, connected segments from USOR3, and these are unchanged, as well as the ruptures with gaps that we smooth out using a smoothing spline algorithm that is applied on either latitude or longitude. For these ruptures, we use average depth to top of rupture, dip angle, etc., consistent with sort of the USOR3 implementation, averaging these parameters over weighted by the area of the different segments. So going over the ruptures now that have gaps, which is the majority of the USOR3 ruptures, we apply a simple smoothing spline algorithm based on a criteria of the change in latitude versus longitude of the rupture, and that decides whether the smoothing spline is applied on latitude versus longitude. We also examine the smooth length of the rupture compared to its initial length. These 3 examples here show the smoothing. We have 3 multi-segment ruptures. The original ruptures is shown in dark blue, and then the smooth version of these ruptures are shown with the cyan dashed curve. And you can see that the smoothing generally does an okay job in sort of preserving the original rupture. These bottom 3 plots are multi-fault ruptures. So you can see the different fault strands are shown with different colors. They do contain gaps. And so wherever we have those gaps, we also go in and smooth them as shown with the black lines. So what we did is we went through over the database entirely, and we sort of computed these, whatever is needed for the implementation, for this simplification of the USOR3 fault ruptures. Then we proceeded in the implementation of directivity. We have used a uniform distribution of hypocenters along strike and down dip, using up to 10 hypocenters along strikes and 3 down dip. For the multi-fault rupture, these are treated differently because we have a hypocenter on each fault strand. So we randomize the hypocenters on each strand. So this is here a simple example of 2 strands. We have fault A, fault B, and the site is here. We put 3 hypocenters on fault A, 3 on fault B. For each fault strands, we compute the average dip angle, Z2R, rake angle, as well as fault-specific magnitude and the RUP to the site. For each hypocenter location, we computed a geometric predictor of directivity for the different directivity models that we've used. We take all hypocenter combinations and we assume that they are all equally likely. Then for each combination of hypocenters, we compare the geometric predictor of directivity, and the full weight is given to the hypocenter with the largest directivity parameter. Okay, so moving on now to directivity models that we have evaluated. we evaluated the true ends footage 2013 direct point parameter DPP model. So we also, Brian Chu developed new model coefficients for us for each of the remaining 3 NGA West 2 models. So this directivity model has coefficients that are GMPE specific. The other ones just apply to any of the directivity models. We also evaluated Baylis and Somerville 2013, as well as its update 2020 model. We've evaluated Watson-Lamprey 2018, and then the Rochandel 2020 model. Just a couple of points here that are relevant to the directivity models. First is centering, and we know that centering of a directivity model basically refers to the model predicting an average null change in the ground motion over all azimuth at a certain distance from a rupture. So basically that ensures that the model does not on average change the magnitude or distance scaling that are inherent in the GMPE. For the models we've evaluated, the Chu and Young's 2013 model is the only model that had what we call explicit centering, which means that we actually calculate the average DPP in a rate track, and then we calculate the change in that delta DPP at an individual site. So this is explicitly centered using a simplified functional form in order to sort of not make the calculations very difficult. The other models, we use them as they are, and we assume that they are centered to the degree to which the ground motion residuals that were used in the model's development are centered. And this is referred to as empirical centering. In terms of aleatory variability, we have some expectation that should be reduced if we correct the median of the ground motion to include directivity effects. In our implementation, we used whatever was recommended by the different directivity modelers, and this has generally been found to have a pretty small impact on the ground motion. So the change is relatively small. For Baylis and Somerville 2013, there was no significant change. The CY14 model does incorporate this effect in the aleatory variability, but no additional adjustment was applied to the rest of the models. BSS 20 has we implemented the change that they had, which is relatively small, as well as the Watson-Lamprey 2018 model, which incorporates a reduction in the aleatory variability and an increase in sigma due to randomizing the hypocenter. Okay, so we have done an extensive evaluation of the models, both in terms of simple deterministic comparisons, more complex structure, deterministic comparisons, as well as probabilistic testing. Based on that, we have selected 3 models to use. The Chu and Sputage 2013 model has a weight of 0.5, and the 2 Baylis et al. Models have a 25% weight each. We kept the original Baylis and Somerville model just because the new 2020 model was still very new at the time of our implementation. And we kept both old and new versions. The Watson-Lamprey 2018 model, we did not end up using it because it's simply a reparameterization of the Chu and Sputage model. And since we include the Chu and Sputage model, we wouldn't include its simplification as well. The Rochandel 2020 model, we didn't use it because of project timeline and complexity of implementing this model. So certainly in the future, an update to this study would look into implementing other directivity models that are available. So let me now show a quick example implementation out of the 19,316 sites. I'm going to show the results for this site here in Southern California, shown with the blue triangle. If we zoom in to see what faults are nearby, this is the site. We see that it's really within 5 kilometers from the San Andreas fault, as well as also close to the Garlock and the Big Pine faults. So when we look at the hazards from this site, the first plot on the left is the no directivity hazard for VS30 of 760 meters per second at a period of 3 seconds, because this is relevant for directivity. We are looking at the total hazard in solid blue, the hazard from graded seismicity in this dashed blue, and then the hazard from the fault sources in the curve with the symbols. And we can see for this site that the hazard is entirely dominated by fault sources. And so if we break down the hazard from the faults into contribution from the different parent faults in USER3, we can see the top contributor here, about the top 15 of them in this list. And we can see that the largest contributor expectedly is the San Andreas fault. If we look at the aggregation of the 2475-year hazard, at 3 seconds, this also same conclusion we see here. This is fractional contribution to hazard, not percentage, but we see that the hazard is dominated by the magnitude greater than 7.5 and at close distances from the San Andreas fault. So now we look at the hazard with directivity. The first plot on the left is for a period of 3 seconds. We have the no directivity hazard in black. Then the directivity from the 3 models that we're using is shown in the different color curves. And then our weighted hazard curve with directivity is shown with a dashed cyan. So we can see at 3 seconds that there is a spread among the different directivity models in terms of hazard. If we look here in the second plot, this is hazard curves at a period of 5 seconds. Similarly, we see that the 3 directivity models are leading to differences in the hazard curves, and then the weighted model is shown in this dashed blue curve. Now, if we look at UHSs, we have here the top plot is the UHS at the 475-year return period. So we have no directivity, and then at the long periods, we start seeing the directivity, the UHS with directivity from the different models. So we see some difference here. In the lower plot, we're looking at the basically the directivity adjustment or the PSA ratio of ground motion with directivity to that without directivity. And that really makes it very clear in terms of the difference observed among the models. We have the Chu and Sputage 2013 predicting a pretty small change in the ground motion. We have the Bayliss and Somerville here in blue. It has the broadband feature, and it goes up to 20% in terms of increase in ground motion. The BSS 20 is narrow band and it's shown in green. And then the weighted version of the ground motion is shown here in dashed blue. These are the same plots for the 2475-year return period. We see again similar kinds of differences amongst the models. Of course, the directivity adjustment is bigger at the longer return periods. And here is the 5,000-year return period UHSs and directivity adjustment factors. Of course, not all the sites had this kind of difference among the directivity models. Some sites had predictions that were from the different models that were more in agreement, but we have seen some differences in the models, and this is why we've included more than one model to capture the epistemic uncertainty in the prediction of directivity adjustment among models. So for our statewide implementation, we had run the hazard at all sites for VS30 of 760 meters per second and default Z values. We've run all of this on AWS because it takes quite a bit of time to run it. So we apply the directivity only on crustal fault sources. We do not apply it on a subduction source or graded seismicity. And our goal was to take these results, generate directivity adjustment factors for VS30 of 760 meters per second, and then use them for other site conditions. So to do that, we actually did some extensive site testing. We selected about 200 sites across the state, computed hazard with directivity at all our VS30 values between 180 and 1100 meters per second, and compared the directivity adjustment factor or ratio at different return periods between 50 and 10,000 years obtained from the different VS30 values. These are just some examples shown for one site. On the top is the directivity adjustment factor for different VS30 values for different return periods. And on the bottom is basically the ratio of the directivity adjustment at the site-specific different values of VS30 to 760, we can see that the ratio is within plus and minus 2%, and that was generally consistent. We found differences within 2 or 3%, which tells us that the adjustment at VS30 of 760 meters per second is applicable to other site conditions. We did find a few cases in Northern California where this difference was a bit bigger, and that's because of significant contribution from subduction sources. And for those cases, we ended up going back and running the directivity for all VS30 values. In conclusion, we have computed the hazard at all these sites with and without directivity. We have generated directivity results for the weighted version of the directivity models, as well as for each of the 3 models. We have also computed the hazard for fault normal and fault parallel using the Baylis and Somerville 2013 model. It's the only model that allows the calculation of FN and FP. And so Sylvia kindly took all of these terabytes of output data and made something very useful out of it, and she's going to talk more about that. But essentially, we have maps, we have user interactive tool that allows the user to really kind of calculate the hazard at any site for any VS30 value. And we have a series of 3 reports. First describes the implementation of the hazard of just a hazard calculation basically without directivity. Second report details everything about the directivity implementation and results in the hazard analysis. And then the third report documents the generation of the maps and the user interactive tool. And that's it. Thank you.
Thank you, Linda. I appreciate that. Before we go to Sylvia about interactive tool that you can download various maps or access all the data, we have few minutes. If you have any question, please enter it into chat and I'll pass it to Sylvia. Sylvia, you want to go over the questions?
Yes, so we have 2 questions and we've allotted about 5 to 10 minutes for these questions on Linda's work. Remember, if you have questions on this work, we can also discuss it at the end. So Kyle Withers from USGS has a question for Linda. Did you compare just the effect that fault smoothing has on hazard without directivity? Kyle, if you want to unmute to discuss, you can.
The only model where we implemented the sort of the user 3 fault ruptures as they are was the Baylis and Somerville model, because initially we started the implementation for Baylis and Somerville before smoothing. I think what we have observed that there was a very small, if any, impact on the sort of the hazard results just for that model. For other models, we didn't compare just because of, you know, the Baylis and Somerville 2013 model is pretty flexible and simple, and it allows you to do different things. But for other models, we didn't do that. We just calculated the hazard with smoothing. So I guess the smoothing impact was pretty small if we just look at the Baylis and Somerville, which is the only model we have comparisons for.
Okay, thanks, Linda.
Sure.
And then Bob Bachman has a question, whether you have linear plots that compare the non-directivity spectra with the directivity spectra?
I don't have linear plots. I have always log x-axis, but I have, yeah.
No, Sylvia, you have it in the online tool?
Well, I'm happy to answer that one. So in the plots, the hard prints, they're actually log scale, but I actually give you tables if you want to plot them linearly. But the other thing is you can look at 2 things. One is we do have plots of the ratio of directivity to no directivity, so you're able to see it there. Also, the directivity amplification, the directivity analyses are done at 0.5 seconds and above. So if you plot that in a linear scale, it's going to be not so hard. It may just not do justice to the ratio. But what I would recommend is, 1 is, yes, you can plot it. 2 is look at the ratio. I think that gives you a better idea of comparing the 2 as well.
Okay. A little tech challenge to do that, but maybe there'll be somebody out there that can help me.
Yeah. And wait, I think in the I'll see, and I can do that in the tool itself. Yeah. So the maps are all pre-generated data. I've got thousands, actually millions of plots that I'm still generating for the hazard and the aggregation, but the tool allows you to change the axes to linear, and whatever combination you want. Actually, so the site-specific tool, I have put that in. If I haven't, I will. Just so that you can visualize it linear. So that's a good place to do it. Okay.
Very good. Whew. If there's any other question, there's another question.
Alex has a question, and Armin has a question. Alex, do you want to just unmute yourself and ask the question? It's faster than me reading.
Sure. Yeah. Thanks, Sylvia. So this might be a little out of scope, so feel free to bypass this, but I was just wondering if you could discuss at sort of a high level the modifications you made to HAZ45 to include the seismic source characterization for USURF. Do you just bypass kind of the MFD input and
right.
Yeah,
we bypass all of that MFD, moving the rupture over the fault, all the traditional ways of when we had just a fault and we had to generate those ruptures internally within the hazard. So we don't have that. In fact, it's quite simple, because all we have is you just read in the ruptures along with their rates. You read in the magnitude, the rake angle, the sort of the points of that form the rupture, etc. And so we in fact have three programs. We have one program that just reads all the USURF 3 ruptures and keep for one site whatever is needed. We are using ruptures within 300 kilometers for each site, as well as calculate all the sort of distance parameters and every other parameters that's needed by the GMPE. Then in the hazard program, we just read the list, but now that list has distance parameters and other things, and the rate of each rupture is read in.
Mm-hmm. Oh, very cool. And Cascadia, I guess, is probably more traditional.
Right. So we kept the features from the original HAZ45 that allows you to use sort of fault ruptures in the traditional sense. You have a fault and then you put ruptures on it according to the magnitude, frequency distribution and other things. So we are able to do both types of ruptures right now.
Very cool. And then the last question related to that is, would this modification to HAZ45 be available to the public, or is this proprietary?
So right now it's not available. I think we have to discuss some more before we can make it available. We have to make it a bit more user-friendly and sort of do more documentation and things. So
and also getting the approval of the funding agencies.
Of course.
But eventually it will become available to public, hopefully soon.
Very cool. Thank you.
Sure.
Thank you, Alex.
Great questions, Alex. One last question from Armin Bebamzadeh. Could you please elaborate further how directivity was considered for the subduction interface?
Yeah, so we did not apply directivity for the subduction interface. It was only applied for crustal fault ruptures.
And then, Linda, you want to elaborate? So what did you and Nick, you did for Northern California, very northern side of California?
Yeah, so for the no directivity hazard incorporates the subduction interface source, but when we apply directivity, it only applies to the crustal sources. So basically for Northern California, we have the subduction interface and intraslab sources based on the USGS model, but that does not incorporate directivity. That's something that can be evaluated in the future. I don't think there has been any studies that at least I'm aware of that have implemented directivity with subduction sources.
Especially NGS sub and directivity, not yet. Very good. If there is any other question, if no other question at this time, as Sylvia said, we still have time at the end for discussions. Otherwise, let's go to Sylvia. For the first time, we are incorporating directivity, non-directivity, USURF 3, and NGFS2 for the state of California. And Sylvia now is going to talk about reading and uploading and downloading all the data maps. Sylvia, welcome.
Thank you. So my job, so I'm going to be presenting on the data sets and the interactive tools. And my job was to take 1.3 terabytes of data that it took me about a week to download and make directivity modeling accessible and usable. And so really taking the data and pre-processing it and post-processing. The main intensity measures that we're interested in, and Linda has talked about these already, and you'll see these again and again in the maps and the tools, are the PSA without directivity, and that's nothing new except for that it's a great statewide implementation of the USRF3, but the most important data is the spectral accelerations with directivity. Using those two data, then I computed these directivity amplification factor. And what's wonderful about these three sets of data is that you can do different types of analyses. Most importantly is you can, if you've already done a PSHA for your site, you can still use these data by using these directivity amplification factors and apply them to your spectra or your hazard curves. The data is broken down into these 19,000 sites. We've got different data for VS30, oscillator periods, and the different hazard levels. And so I'll have these intensity measures broken up and grouped by locations, as well as just different data sets. And I did also post-process the DeAggregation data. And all this, Linda has already talked about and shown you these. So there were pretty much three levels of data that I was working with. The very first level is the raw output that comes from HAZ45. I don't know if you guys have seen this type of data, but it's wonderful. You see a screenshot here at the top. You open up a file, you can actually visualize it and see it, and things are lined up perfectly. But it's really hard to automate the processing and the management of this data for all these sites. So what I did is I processed these data and grouped them and placed them into HDF5 files. The nice thing about HDF5 files is that they're self-documenting, and it's ready. It's easily accessible for programmable. You can access it through Python or whatever program you have. So this data is grouped by different intensity measures or different locations, and there's just a lot of different sets of data. But then we wanted to make this accessible to the human and being able to evaluate the effects of directivity. And so we generated some post-process data where I've already mentioned we've got these interactive tools for the PSA with and without directivity, these amplification factors, and some DeAggregation data as well. So there's three types of this data that we have. I like the number 3. We've got the geographic distribution of the intensity measure tables. So tons of CSV files that are grouped. You got lat long and then the intensity measure depending on different site data. We've got UHS tables, and I think I also have hazard curves. And again, that's something that's easy to access just by a computer. Then we've got the maps. We've got some static maps, which are great to put them into a report. And that's where I started with. But then Linda asked, oh, but can you tell me a little bit more about that red circle next to the green circle? And that led to developing these interactive maps where you can actually zoom in and question the data itself and understand better what is each point and where it's located and more information about it. So that's where these interactive maps started from. And then the ultimate goal was to develop a tool where a user would specify latitude, longitude, and a VS30, and then the tool interpolates from nearby sites. It depends on, it could be 1, 2, or 3, or 4, depending on the location. And we can get UHS with and without directivity, as well as the UHS directivity amplification factors, which is what I was referring to for Bob. If you want to just look at those, then that gives you a better quantification of the amplification due to directivity. There's also DeAggregation for the nearest sites. And this allows you, again, to compute the UHS with directivity using your own user-specified directivity weights. So you can take the data from here, apply it to your spectra, but if you're not happy with the weights that Linda chose of 0.5 0.25 and 0.25. You can actually adjust. Maybe it's one of them applies better to your special case. And so you can actually select the different weights for the different directivity models. So we made it as robust as possible with as much flexibility for the user. And that's what I'm going to talk about now is these maps and the tool. Excuse me. You can access these through this website. I'm working on getting a DNS, something easier to access. But if you just Google California Directivity UCLA, you will find this is the main page for the tools. And then there's access to each one of the tools that you want, whether you want the maps or the interactive tools. The static maps are accessible directly from the interactive maps, so I didn't have too much bookkeeping. With the interactive maps is handy because you can zoom in, zoom out, and there's additional features that I will show you, and you can visualize all these different intensity measures. Here's an image of this maps. This is where it all started. I plotted these to just kind of get a good visual as to what is the effect without directivity. With directivity, the amplification, where are the hot spots in California? And it's actually pretty cool and interesting to look at the data. You can zoom in and get a feeling for, if you know the area. San Francisco is the easiest one to actually see. You've got the faults, and so you can zoom in to these pages and do some visualization. But we wanted to step up our game, and so we went to these interactive maps. You can access these interactive maps from that web page that I gave you, as well as this direct link right here. This is interactive visualization of static data. I'm not doing any computations. Everything comes in pre-computed, and everything is grouped depending on the different maps. The files may take a couple of seconds to upload, only because there's over 19,000 points, but they're actually pretty fast. And once it loads up, you can navigate very easily and very fast. At the very top of the maps, you've got these pull-down menus. You can look at, and as you can see on the very left pull-down menu, which is what the data that is being mapped, you can look at the spectral accelerations without directivity or with directivity, as well as a comparison and the same map of with and without directivity, as well as the amplification factors, the recommended one that has a lower bound of 1.0, or just the weighted model that doesn't have a lower bound of 1.0. We've got the different amplification factors for all the different models. And then we also have just site data and information that you have that was used for the analyses. The oscillator period, it's got a selection of all the periods all the way to PGV. Everything that was in the analyses, I try to keep in here. Now you'll see that 0.5 and above is green, so that menu will pop up if you have the case for directivity. If you're also looking for no directivity, then you'll also have the option for less than 5 seconds. Anything less than 5 seconds, the amplification factor is 1, and the with directivity is set equal to the directivity values. So it was just easier to just let you choose what you need from these pull-down menus. There's different options for the different VS30s, as well as the different return periods. And so you pretty much click, make your selection of the pull-down menu, and every time the pull-down menu gets updated, this map here gets updated in real time. So it's very easy to navigate. Here's an example of the data maps. So we've got the VS30, the site-specific VS30 that Linda talked about based on the estimated VS30. You can learn more about that in the report. There's also the estimated values for Z1.0 and 2.5 were available. And so the map shows you where these locations are. You can actually zoom in as you hover, it will give you the numbers. And we also have a map of just the USURF3 faults. This map of the USURF3 faults is actually always in the background of all of your data, as you can see here. So these are useful maps to really understand what were the assumptions that were made during the analysis. I'm going to zoom in and show you one of the options that you have here, and this applies to actually all the maps. I'm just using this map to make it easy. So this is for the USURF3 faults. If you hover over a fault, it gives you the name. If you click on it, it gives you a little bit more information. And then every map has a little button here that says click here for static map, and it opens up the static map in a separate tab. There's also a button at the very top here. Let's see if I can go back up here that you can say open map in a new tab. And so this actually just opens up that individual map in a new tab if you want to look at different maps at the same time on your browser. And then we also have different types of backgrounds. It really depends on what you're looking at. Sometimes a plain map is the easiest thing to visualize your data, but sometimes you want more information about the geography of your site. And so I figured I'd put these in because sometimes it makes the data that much more interesting and easier to understand why you're getting certain patterns where. And these are options in all of the maps. Then we also have this additional data in the layers, not just the USURF3 maps, but we've got the California natural gas pipelines, as well as the CEC storage facilities, so that the original supporting agencies can actually access these data and do some quantifiable analyses with their locations. So these are always in the background of all the data. So these are layers that are always accessible. I've added some simple map features. You can add your own markers so that you can understand where you are, where your site is located to the faults or to the study site. And you can actually then measure. There's a little measuring tool in these maps. These are all available in all the maps, and you can zoom in and out with buttons, or actually I set it up that you can zoom in and out with the wheel. So as you can imagine, I've set things up really nice that you can do a lot with the data. So here's an example with the SiteSpecific VS30. Again, you can click here to visualize just the JPEG, but here I am zooming in. And if you zoom in, you can actually, as you hover over, and these are just screenshots, but you can actually get information about each point. And then if you click on a point, it gives you the uniform hazard spectra for that site and that VS30, as well as hazard curves for the period that you've selected in the pull-down menus. And then it gives you a bunch of tables that you can just open and close in this little pop-up window. So it's a very busy pop-up window, but I wanted it to make sure that you've got access to all the data in one location. So I started with just basic values, and then we added these data up. I'm still generating a lot of these maps because, as I said, it's millions, but as with time, the data set will grow. And then, excuse me. Then we've got these different quantities that you can actually visualize. We've got the no directivity. With no directivity and with directivity PSA, as well as the directivity amplification factor. So this is when the maps get fun. You can actually hear every scenario, so every intensity measure, you've got at least 6 maps. You've got the PSA with no directivity, PSA with directivity using the amplification ratio of 760. Linda had talked about this in her presentation, that the directivity calculations were all performed for all sites at VS30 equals to 760. There's a region up in the Pacific Northwest where the amplification at different VS30s was slightly different because of the subduction influence, and this is something you can read about in the report. So we actually have, they recomputed the PSA with directivity using the site-specific or the different VS30 values. So we have that data as well on the maps. I kept the 2 maps separate so that there's no strange discontinuity in the maps, but maybe if you're interested in this region itself, you might want to go to these maps themselves. Same thing with the amplification ratio. So we've got the ratio at the VS30 itself, the ratio for VS760. And then, as I've mentioned before, we apply a lower bound of 1.0 to the directivity amplification factor that we recommend, but you can also visualize it without lower bound. And you can see in these regions up in the northeastern California, there seems to be some de-amplification. So the directivity is less than without directivity. And so this is something that needs to be looked at, but we figured we'd put it in the map because the data is there and it's something that helps you to understand what's going on with directivity. I also added recently a map with and without directivity on the same map. So this takes a little bit longer to load because it's double the data. And what I've done is you've got the circles, the inner circle is with directivity and the outer circle is without directivity. So you can turn on and off it within the same map. What are the effects? If you're zoomed in, it makes it a little bit easier to see the effects of with and without directivity. Otherwise, we actually have separate maps for the two as well. And then here, just to kind of show you the amplification factor that I was mentioning before, we've got regions where there is a de-amplification up in these regions here where it's pink. I've made an effort to make sure that all the PSA values for the same with and without directivity use the same color map, as well as these amplification factors. For each scenario, they have the same color range. So it's easier to compare the different amplification factors for the different models. If you then select a site, now you really get a lot more information than even in the VS30 map. And this is in all these maps when available. You've got a spectra with and without directivity. You've got hazard curves with and without directivity. You have information about the deaggregation, as well as hazard curves split between source type, as well as the parent fault. Linda showed you these plots. And so I've been generating these for all the sites. And then I've actually put in tabulated values for the spectra. If you want to use them yourself, you can actually go here, pick a return period, and just, this is just simple text in HTML, and you can copy these values and these tables and put them into your own Excel sheet. So I've tried to make the data as accessible right where you're at when you're looking at it globally, as well as locally, and that's where these interactive maps came in handy. It's kind of fun. You can then start playing at the effect of the return period, as well as the effect of your oscillator period. And it's fascinating data because you got to keep in mind that this is not a deterministic analysis. This is a probabilistic analysis. So there's a lot more involved in these data than just a simple model. And so it's interesting to look at the data at a statewide as well as locally and see where the hotspots are in the region of interest. And there's also the analyses were also done for the VS30, the site-specific VS30, where things get a little bit more mixed, but it actually shows some really interesting data as well, because then you can almost see what's a little bit more realistic than for the same VS30 across the map. So there's just a slew of about, I think there's about 6,000 maps and different options and combinations of maps. Or I think I'm at 9,009. So it's fun to play with these. And it's just, I find it very useful in really understanding and quantifying the effects of directivity in different regions of the state and how that's impacting your local sites. The next step was the main goal of the project was to develop this interactive tool. This is very similar to what it did for the NGA subduction. It's the same type of website. So it's very intuitive. And what the tool does, it interpolates the UHS to your user specified location and VS30, and it computes the directivity amplification factors based on your own selection of factors. So that's how the input works. You input your site coordinates or your VS30, as well as directivity weights. I like to use integers, but if you want, you can make this 0.25, 0.25, and 0.5. These are the numbers that Linda was giving, or you can set 100 if you only want to use the BS13. If you want to use the 2020 model, then you can just put a 1 in this and zeros everywhere else. And then you have the option as to whether to apply the lower bound of 1 to the adjustment factor or not. These are done ahead of time, so that's why I'm having you have this input because they're done in the processing. And then you choose the return period for your uniform hazard spectra and your oscillator period for the maps, as well as your deaggregation. So you put in this input. Right now, I've put this temporary password. As much as you need to log in and create your own account, if you have an account with the NGA subduction portal or with the tsunami portal, you already have one. But right now, put in this temporary password because you're the first people to really test this. And but I'll be removing this password soon. But right now, 1979 is what you need to input into this box if this box is there. So once you click run, The program goes in, does its computations and interpolations, and as you can see, it grays out the site and the hazard data. If you want to start over, if you want to change those inputs, you have to start over because it's a workflow. So those are predefined values. I allow you to then play with the directivity factors. But once you click run, you go and you look at the maps. What I do is I plot the location of your site as well as the 4 sites. In this case, there are 4 sites that are going to be used for the interpolation, and this is the faults that are there. It's the user fault. So you can actually get a little bit of information about these data. And then on the right-hand side, I've got the same interactive maps that I showed you before for your return period and your oscillator period. If you want to put your site into this big map, you have to do it manually, just as you done it there. It doesn't automatically does it because it's across platforms. But I thought this would be helpful in really getting a visualization as to where your site is. Once just as you scroll down, you'll have 2 sets of spectra, the no directivity. And Bob, for you, I will bring back the option of log and linear scale. I can do that. And so what you see is I plot the spectra for the 4 different sites. It gives you the weight, distance weight that was used. And then it has 2 different spectra here. One is the weighted average and one is the envelope. The weighted average is by distance, and then the envelope is the maximum spectrum, right? So you may have one site, for example, here, 9921, that's the closest to the fault. And so what the program does is it computes the coefficient of variation, and there's a little note here that I zoomed in, for a specific case. And it says, if the coefficient of variation of the spectral acceleration is higher than a certain limit, we recommend using the envelope because we don't really know exactly where you are in this geography here. So right now, in this case, it's recommending you to use the envelope spectrum, the highest value. What the program does, it uses that spectrum as the no directivity base for the directivity calculations, applies the directivity amplification factors, and it gives you a spectrum with directivity. It shows you the no directivity as well as the different models. On the right-hand side, it shows you what the ratio is between them, and so you can actually visualize it a little bit better to see what the amplification is. And this is what Linda was showing earlier. But you may look at your site and go, wait a minute, I'm a little bit more like these other sites. And so if you want this now, it gives you a pull-down menu. You look at your site, as I was saying, and you say, hey, I don't want to use the envelope. I want to use one of these other sites, or I want to use the weighted average. Well, you select in this pull-down menu, you select what you want to use as the basis for your no directivity spectrum. The program, as soon as it gets a change in that value, it goes back and recomputes the directivity spectrum. So in this case, on the left-hand side, I show you that it was using the black line for the no directivity, but what you actually wanted was this curve here. And so by changing that pull-down menu to site 9920, let's say, which is this site over here, it's a little bit more like I expect it to be, more like mine. Then it's using this value here. You see it goes to 2.8 as the no directivity, and it applies the amplification factors because you picked a site, it uses the amplification factors for that site. If you use the envelope or the weighted average, the amplification factors are the weighted average of the for the geographically or distance weighting for the different sites. And that's pretty much the core of what you have here is these 2 sets of graphs. We have additional data that you can now, I give you the numerical data that's in those plots. So you can copy these data and paste it, or you can actually, and I'll show you afterwards, there's a download button where you can download the data. And it gives you a nice CSV file. You can look at the deaggregation plots. This is for the case of no directivity. I have to see if I had the data for directivity. But these are just, you pick, they're just different tabs, and then it shows you the deaggregation data for that one site. We can't interpolate, it's just way too much interpolation that needs to be done. So you figure out which sites, or you look at the different sites to assess what the 2 deaggregation would be for your site. And so I've got the bin deaggregation, as well as hazard by source type, as well as the individual faults, as you see here, San Andreas, again and again. And as I said, these are millions of files, so I'm still generating and uploading these files. There's also the data itself on the amplification factors, as well as, which is what you saw before, and then I have data for the fault Noma fault parallel components for the Bayliss and Somerville model 2013. And so we've got a plot and we've got the values tabulated here for you. Please be careful. Remember that things start at 0.5. So I've given you the entire period range, but the difference is really you start seeing them above 0.5 seconds. Just like always, you can download the data and it gives you a nice CSV file that you can open up in Excel for plotting what you need or not. And that's pretty much it. In summary, we've got these two tools, the geographic distribution of the maps, as well as individual intensity measure tool for your site. The goal here is you can either use the PSA values directly, or you can use the directivity amplification factors to your favorite PSHA results that you like. And that's it. There's a main page. And if you go to the NHR3 webpage, you go to California Directivity, it takes you to the main page, a lot of nice descriptions that I pulled out from Linda and Nick's report. And then there's two buttons, whether you want to enter the maps or the interactive tool. So we concentrated everything to one reference point. And that's it. Thank you.
Very good. Thank you very much, Sylvia. Appreciate that. Also, before we get to discussion and question and answer, so there are 3 reports available based on the directivity based in the state of California. One of them is already published, which sets the stage, is no directivity. The second one is 99% is final. We went through a couple of iterations. Soon we are going to post. And the third one is about the interactive tool, that how you get access to the maps, how you get access to the data, downloading, and so on. So one of them already posted at UCLA website. The other 2 will be posted very soon. Now, any questions, comments, feedback, discussion about the A to Z, from how the directivity-based computation was done and how the maps and interactive tool have been developed, or how you can use it. But the best way to tell you the truth, just go to the link at UCLA website, enter your site, get the results, and so on. This is the first time anyone is doing such a thing, at least in the US, at the largest scale, statewide. Any questions, any comments? And Sylvia, are you going to make available the slides and post it also for the users if they want to take a look at it, especially the tools?
Yes.
Okay.
I'm going to put in these presentations on the main page, as well as maybe a more detailed how-to, but I've tried to make everything as intuitive as possible. So once you get in, there's a good flow.
Yeah.
So
I think there is a question from Alex. Sylvia, Alex, would you like to ask your question?
Oh, sure. Yeah, I was just wondering, by the way, this is extraordinary. So hats off to everyone here. Are there plans for having some sort of REST API or HTTP type of request response to download data outside of just the browser interface?
So the data is all not all of the data, but the maps and the interactive, and I believe I've also uploaded the CSV files. They're all in an S3 bucket in AWS. And so you can actually just the file names, there's a pattern to the file names. So you could just write your own something that can
Just get the,
download what's in the S3 bucket.
Yeah,
So
or
that's
like
why-
the final download, kind of when you get to your, maybe I shouldn't say data, but analysis results, right? That CSV you showed a screenshot of.
Yeah, well, that
Yeah.
one, there's a button at the end of your tool.
Right. Yeah, I was asking if there's kind of a.
So you could do
Yeah.
it for a million different sites.
Well, you could throttle it, but yeah. But yeah, okay, understood.
Yeah, no,
Thanks.
I haven't. It's an interactive, so there could be a way of making this but that would be a slightly extra step, because we want you to go and interactively visualize the data and being able to process
Absolutely.
and make your choices. Otherwise, the user defined data, you can just download it and then do it yourself. So that's a good idea if there's financial support to making things a little bit more accessible. It's always there, but
Yeah, cool. Thank you.
we'll do
Very
what we
good.
can. Thank you.
One point that this is as good as you can get in terms of accuracy and so on, given UCERF3, given NGFS2, given models, as well as directivity models. So if someone wants to do obviously more into that, obviously always is possible. Any other questions and comments?
So I see Ashley raised hand, and then we also have a question from Emra. What is the potential cause of de-amplification in hazard estimates with directivity in Northern California? Any early thoughts? So I can answer that. This is not a sort of a mistake or anything like that. In fact, it is expected that if you are in the back, if you think of one rupture and then the site location, if you are in a location where all the ruptures coming towards you, you get amplification. But if you are in the backward directivity, you could get de-amplification of the ground motion. And so for those sites, I think the explanation is that they are probably in the backward directivity of most of the ruptures nearby, and so you get de-amplification. So one could perfectly well use that if there's no, it's not a mistake or anything like that. But we put an option of lower bound of one, sort of, a somewhat conservative application. Nick,
yeah, I just add, if you're concerned about that region up in northeastern California where you saw the reduction, it's also because those are typically normal faults, dipping faults, and in thinking about the simplicity of directivity models, we all think of strike slip and having an increase in ground motions, but the normal and the dipping faults are a little bit different with regards to the directivity models. So that's another factor. The other issue that was highlighted was this whole issue off the northwest coast of California, where the subduction zone contributes and the difference in the VS30 scaling. So that's another feature. So a lot of that information is sort of written up a little bit more in the reports, but it does make consistent results with the directivity models and looking at sort of simplified representations of that.
I wanted to add. I wanted to add to that.
Yeah, go ahead, Sylvia.
That this is why I'm excited about the maps, because that's not something that would have been easily seen and understood if you're looking at so much data. And so these maps allow you to visualize, what are the different effects of these directivity in hazard. So I'm excited about the questions that it's going to raise and things to think about and understand better with directivity and at hazard levels.
Thank you so much. This is Imra. Thank you very much for the clarifications, Nick and Linda. I wasn't I was just curious whether also, because the area that hazard model captures only includes like the California, if the sources beyond Northern California, crustal sources were included, would that also add any improvement in the de-amplification or balance it? I'm not sure how the faults, crustal sources in the north of Northern California, directivity would improve or add into to the results that you showed today.
So, Nick, you want to say a few words about the bordering,
Yeah.
outside California sources?
Yeah, so there are a couple of things. As was shown earlier, we ran 19,000 plus sites, and that includes not just up to the boundary between California and, say, Oregon, Nevada, and Arizona, but sort of leaking into those other states, and that's to capture basically the USER3 representation. Along with that, in, for example, Northern California, there are faults that start in sort of Northern California, but go into Southern Oregon that are modeled as part of the USER3 source zone. So we've done that to sort of capture ground motion estimates from sources that you would expect to contribute at sites in California. In terms of other faults outside of our sort of selected boundary, they could potentially contribute. However, if you think about it, in Southern Oregon, there aren't many large strike slip faults that would be expected to contribute to hazard in Northern California. The one place you might see somewhat of a little impact would be along the border with Nevada, where you have a lot more of these characterized faults. But it's not expected that for directivity that it's going to be a huge impact, either decrease for backwards directivity or increase for directivity going forward.
Thank you so much. Thank you.
There's a couple of comments on that to follow up from Sean that he's agreeing with Linda, and then Jennifer Thornburg about the amplification. I like to move to the other questions, and then if we want, we can circle back to this topic, which I think is interesting. Ashley, would you like to just pose the question, please?
Or ask it.
Yeah, right. Pose. I said pose. Yeah, ask the question.
Yeah, it's first a thank you. This is a great tool that I think the community and the science behind it, that it's going to be extremely helpful. So thank you for all your efforts. And then I may have missed this, Sylvia, but what was the spatial interpolation technique that you use for the maps? And when you refer to nearby sites, how do you define what's a nearby site?
So the interpolation is based on 1 over R distance. That was something that we agreed on as a group. And so I think, Linda, I don't know if you included that in the report as to why we would do 1 over R. But you can expand on that.
Yeah. So basically, it's a relatively simple interpolation. For a given site, we first locate what are the 4 sort of nearby sites around it, so that make sort of a square or a rectangle around that site, and then we interpolate, as Sylvia said, based on 1 over R. Interpolating the UHSs at this point. That's what we're doing. And then we did quite a lot of testing. Generally, this works well, but there are some cases where a fault could be passing within that rectangle, and so your site might be a lot closer to that fault than all the others. So for those cases, that's where we sort of found that a good proxy to sort of flag that out was how different the UHSs are in the 4 corners. And if they are quite different, then we know that some of them are a lot closer to a fault than others. And we sort of suggest the use of envelopes in these cases. Generally speaking, because these sites are like 5 kilometers away from each other, the interpolation works well. It's just that when there is largely some kind of a special cases, then you might want to use the envelope.
And I picked the 4 sites just based on where the location is and what the closest points. But if I'm on a line, then there's only 2 sites, or if I'm on the edge, well, there's always 2 to 4 sites, depending on that. So
makes sense.
Yeah.
Very good.
I think we have a clarification that Jeff Bayless is that Sean is actually Jeff Bayless. Okay, understood.
My question is the text that I received from Sean or from you?
So is it from Jeff or Sean?
I think this might have been Jeff.
Okay.
Yeah, that was Jeff. Zia, we have we'll let Zia ask the question in person. Go ahead. And then there's another question.
Thanks for the wonderful work. I think this has tremendous effort. My question with Yusuf is, Yusuf, as a reviewer, if I do a Spectra based on this, just no running my own PSHA, nothing, will you accept for a project?
Using this tool, you mean, Zia?
Yes, yes.
To tell you that this is the best that we have. Okay. I'm telling you. The only complexity is that if this interpolation and so on, your site is very close to the fault, then you have to be careful, as Sylvia said it, that instead of interpolating, you want to select the closest computed the site, and so those are the things that if you're very close to the fault and a little bit farther away from one station, you have to be careful about this weighted average of interpolation. But this is the best tool that we have.
Okay.
Very good.
All my work has been cut short quite a bit, so.
No, Zia, then it means that you have to fund us to do more work.
Right. Thank you.
Thank you.
I'm excited that the profession and the scientists can use this tool. So
we also got one question why Shahi and Baker directivity model was not used. So yes, we have nothing against this model or other models. We were a little limited in terms of our sort of timeline and scope. A lot of our effort went towards how do we deal with the user 3 model to implement directivity, and so that took quite a lot of time and effort. So in fact, we do recommend that in the future this model can potentially be evaluated. We tried to select models that were sort of, there was a difference amongst them that that we capture the epistemic uncertainty in directivity prediction as well as we can.
So as Linda said, it's all, to tell you, it depends on funding. If we get funding, we should add Badi Rochandel model as well as other models and evaluate and so on. But as I mentioned, this is the best that we have.
So let me clarify. Sorry about interrupting. So there's one thing which is called the maximum direction from Shahi and Baker, and the other is rupture directivity, which you guys are handling. So I think there are two different things.
Right.
One is the maximum direction factors. I think that will remain in there because the building code requires. But rupture directivity is what you. So what I'm probably looking into it, that apply Shahi and Baker, do my PSHA, apply Shahi and Baker, may come up with the Sylvia's tool to come up with amplification factors for rupture directivity and apply to my PSHA, and that should probably solve the issue.
Right. I mean, we are only here, referring to a sort of directivity, average directivity adjustment on the ground motion.
Right.
Exactly.
Yeah.
Okay.
this is all on the ROT D50, right?
Right.
Yeah.
So that is ROT D100 issue is different, I think, which is Shahi and Baker.
Yeah, Shahi and Baker, they have different things. That ROT D100, as well as they have directivity model that we didn't have opportunity to incorporate.
Yeah, we have a comment from Jennifer Thornburg saying that, please explain the results. There are choices made here. This presentation is just a very high level presentation given the time that we have. There are 3 reports that explain everything and all the choices, and yes, I agree.
You are absolutely correct, Jennifer. There are lots of, this is the result of really 3-4 years efforts, continuous efforts, and there are lots of things going on. Definitely, once the reports are published and obviously the journal papers will be submitted, I'm pretty sure the reviewers of the papers and so on, they ask, so what did you do about this? So, which it has huge background. That you're correct. We have only 1 hour presentation. That doesn't mean that we did a decent job of all the details.
Well, I think what Jennifer's coming in from is she's asking Zia to document what Jennifer, I don't know if you want to speak, but my interpretation is, as she's added, it's you as a user, what choices, you've got so many choices here, what were the choices, and being able to document your choices. Do you want to speak up, Jennifer?
That's
anyways,
fine.
so
I think that was a good point.
I can try. Yes, absolutely. That is what I mean. You have allowed a lot of different choices in here, which is terrific. I just want the users to show me how they're using the tool and what choices they've made.
Absolutely. This is absolutely clear.
Thank you so much for this tool. It will really be valuable. No question about it.
That's why it was important for us to give you the flexibility of this is what we recommend and these are the weights that we used, but then you've got the flexibility to do your own adjustments that would improve your site-specific study versus a statewide study.
Very good. Anything else? Do we have anything else in the chat? So we really appreciate it. I'm telling you, moral support is extremely important because really no one is making any money out of these things and so on. But appreciation and moral support gives us energy to keep going, really.
Yeah.
Thank you for all the nice comments. Any other questions?
There's Jongwon has a comment that he thinks that Mansoor was referring to a different paper. There's the one on the directivity effects. But also I wanted to add, while I have everybody here, please provide feedback on the usability and issues that you may run into with the tools. Of course, we're always looking to improve them. But I think there's a couple more questions here. Two Shahi and Baker papers, one on directivity effects, the other one on directionality.
Yeah,
and so I think it's the directivity model that he's referring to.
Right.
Can I ask another question here? First of all, I'd like to thank all of you, Linda, Nick, and Sylvia, Youssef. The great job as a practitioner. This is very, very useful tool. And just looking at the list of sponsors here, mostly from energy sector, and I see K-Trans included here, so that kind of indicates to me. So maybe this can be incorporated into their seismic design criteria down the road, and possibly this outcome can be adopted by the other authorities, like in the transportation sectors. For example, LA Metro and here in San Francisco authorities. I wonder if if you have any plans to contact the other authorities and see if they're interested in adopting this tool and this study results, because most of the design criteria they go with a very crude approaches to incorporate this near fault effects. So I'd like to hear from you guys if you have any plan on this. Thanks.
So, young one, thank you very much for your comment. It's similar to any other things that we have been doing in the last 20 years. For example, like NGA models, we are going to develop, we are going to make it available to public. Then it's up to agencies like USGS, California Geological Survey, and others to adopt or not to adopt. Obviously, in fact, it's their decision to evaluate, and they can say that, oh, by the way, we are going to adopt that feature of this work. That's fine. So definitely, we don't want to get to the other side and lobby for adaptation. We like them to review and adopt, or a part of this to adopt. So the main funding agency for this task is coming from California Energy Commission, because Sylvia also showed you put natural gas pipelines in the state of California, and then you see where, for example, you get more effect or less effect of these things. However, always Caltrans, PG&E, SoCalGas, and LA Department of Water and Power, they have been contributing to this effort as well. But that doesn't mean that, for example, high-speed rail tomorrow there is going to adopt anything of that. We'd really like to leave it for them to decide. Very good. That was good comment. Any other things? We have only a couple of minutes, 2-3 minutes. Any other question or comments from anyone? Otherwise, I really like to thank Linda, Nick, and Sylvia. They spent a tremendous amount of time in the last 3-4 years, And we are really hoping even we keep continuing working on that, adopting other models and so on, and expand it like anything else we have done. Otherwise, thank you all of you for coming here. Stay in touch. If you have any specific comments, questions in the future, send an email to one of us. We will share it and we will be in touch. Thank you. Thank you.
Thank you.
Thank you, everyone.
Thanks.